In stats, we introduced the t-distribution on Tuesday. Before we do that, let's look at a typical problem that we've worked in the past. So it's at the very top of the screen, and a sample mean problem is given to us where we have let me write population here. We have some population stats. We have an average bill of 187.50 and a standard deviation of 54.50. But then look at the next sentence. A sample is taken and then it asks the question, probability that a mean from that sample, so our question looks like this, is greater than 200. Now we had a problem like this very problem a couple weeks ago. And since it's a sample mean, X bar, it's a sampling distribution problem. N is greater than 30. That tells us the sampling distribution is approximately normal. That's all because of the central limit theorem. So we talked about that very briefly, and that's all because I wanted to talk about it more today and in the next video. So we know it's normal because it's a large sample. In the last handout, it was a proportion problem, and that's a large counts condition. So that's this condition. If it's a hypothesis test, you leave it like that. If it's a confidence interval, you put a little hat on it. But if we're talking about means, right here and right here, it's the central limit theorem, this concept right here. If n is just plain old large, larger than 30, we can say it's normal. All right, so that's a little bit of review. To answer this, you have to find the new standard deviation. You kind of luck out with the mean because it stays the same. But the new standard deviation gets altered by that sample size because you have to divide by the square root of 50. So we had this, it was in Sampling Distributions, Chapter 7. If you're mixed up, or it's on the formula chart under sampling distributions. So we would get that standard deviation right there. You'd go get the z-score of 200. Then you'd use normal CDF. And after all that, you get a final probability. So we've done that many times before. In this handout, we're missing something that was given to us in the green writing. So let's see, when doing a real experiment and conducting hypothesis or confidence interval, typically we don't have the population standard deviation, sigma. Typically we don't have that. Typically, we only have S, the sample standard deviation. Which, according to what we're about to talk about, we're not allowed to use Z if we only have S, because S is really variable. Like sample to sample to sample, it's going to be different. It's not 100% accurate. Because if I take another sample of 50, it's probably not going to be 54.5. If I take another sample of 50, it's probably not going to be 54.5. It's going to be close to it, but probably not exactly that. So sigma is the perfect value, and in an ideal world, we would have it, but yet we don't know it because we're not psychic. We have to take a sample, hence the whole reason of doing statistics. We are going to use something called the T distribution. There was this guy named Gossett. He was working at Guinness Brewery, and he was trying to perfect the brewing process. This is real. You can Google it, look it up. Gossett was really doing this. And he was very good at math. And he was using the Z-curve for the formula and all his calculations, and it just wasn't quite working. He ended up deriving a new distribution called T, and it's based on S. T is based on S because sigma is unknown in a typical problem. So that right there is the key. Notice I made it very bold and larger font right there. When sigma is unknown, we are going to use T. That is the whole reason right there. He was very proud of his work. He discovered this T distribution. There are actually infinite T curves because it's dependent on the sample size. And he wanted to publish his work, but yet he didn't want to reveal all the secrets of Guinness beer. So he went under the pseudonym Student, and he got his work out there. So it's kind of a cool story. So what is T? What did he find out? I'm going to draw it here. Let's start with Z. Let's let this green curve, that's decent, be the Z curve. And let's let this black curve, if you can call it a curve, be T. So T is more variable than Z, and that's because it's all based on S. It's not based on the perfect standard deviation. So it's a little bit more erratic. It's more variable, more spread out. T is dependent. Or no, let's back up, sorry. T is dependent on degrees of freedom. That's what this thing is talking about constantly. And degrees of freedom are based on the sample size. And I type more on the next page about that. So degrees of freedom is directly related, dependent on the sample size, which means there are infinite T curves. If the sample size is huge, that black curve is going to approach the green curve. If the sample size is tiny, it's going to be a lot more spread out than the green curve. And that's what all those properties are talking about. Ultimately, you just need to know how to read Table B. So let's practice that right here. Table B, it gives us all kinds of critical values. And like I said yesterday, you can read it two different directions. So if I'm reading this table from the bottom to the top, I can use it as a confidence interval. Top down, the typical way you read, is a hypothesis test. So if I'm reading from the bottom up, notice I have my confidence levels. Yesterday we looked at that number, and that number, because the infinity row is Z. And notice as degrees of freedom, Look at, for example, the 95% column. As degrees of freedom increase, what are all of, let me draw an arrow. What are all of these numbers approaching? 1.96. It gets closer and closer. Look at 1,000 degrees of freedom. It's almost exactly 1.96. And then look at the top. It's very variable. A large t-score. All right. So on our notes, let's practice. If degrees of freedom is n minus 1, that means on this first question, df is 12. Find t. So you go to the formula chart, go to the 95% column and 12 degrees of freedom. We are looking, it's hard to do without zooming in, right there. 2179. This next one, df is 20. Go to the 99% column and go to the 20th row, and you see 2.845. If degrees of freedom are insanely large, larger than 1,000, we're just going to use the bottom row, the infinity row. All right. By the way, this table is very limited because it's not infinite, like they didn't have all the space in the world. So if we have 32 degrees of freedom, I'm looking right here, they didn't print that row just for the sake of space. So in stats, we want to be careful. We don't want to overestimate anything. So we're going to be conservative and not overstate what we sampled. Because if I was to round up to 40, let's go back to the chart. Notice it skips 30 to 40 to 50 to 60 and so on. So we don't have 32 there. So we're going to be conservative and just round down to 30. All right. 2.042. All right, we're going to try a confidence interval. So it's very similar to one proportion Z interval. You're going to lead by describing what you're estimating. You're going to walk through the plan step. Needs to be a random sample. Needs to be small compared to the population. This right here is a little different. Not the large counts. Because we're not talking about proportions, but central limit theorem. If n is greater than 30, we're good to go. Now, there are more conditions in there we're going to talk about. Here's our formula that the calculator does right when you press calculate or OK, and you'll conclude like we did before. So let's give it a shot on part A. Maybe hit pause and see if you can do some of the steps. Like, for example, mu, the true mean of whatever. And then walk through the plan step. All right, I'm moving on. True mean, usually you can copy it from the prompt, and I'm looking right here. All right, there's the beginning. Skim through the paragraph, and you see that we had a random sample of 40. Um, 40 is greater than 30. Sampling distribution is approximately normal. Now, you have to kind of imagine on this one that if we're talking about these vehicle engines, I bet it is safe to assume 40 is less than 10% of all of those engines. Like if we're talking about Ford cars or something, one type of car, 40, that is definitely smaller than 10% of all those cars. Then those are our 3 steps. Let's dive into a T interval. Now be really careful how you write your notation on the values they gave us. This right here is X bar. Notice these 2 values are talked about right after it says the sample size. So those are sample values. They are statistics, not population values, which causes us to do T because that's S and not sigma. All right. Degrees of freedom is 39, and we grab our calculator. So in the calculator, we are going to look for a T interval. Whoops, wrong button. And once again, this is because we have S and not sigma. See where the arrow is? I should change colors. Because of that right there, that is forcing us to do T. That's what Gossett discovered through all his work and experimenting. All right. So we go to T interval. You have 2 choices here. If you click data, that is like this problem. You have a list of data values. But we have statistics given to us in this problem. So click that, pick stats, and OK. All right, we have 1.2675, 0.3332, and 40, and 95%. And you're done. There's the lower and upper. Let's wrap this up. 1.1609 up to 1.3741. We have 95% confidence that, now just look at your title of your work, that the true mean, and you're just copying now, amount of NOx emitted by light-duty engines of this type is within 1.1609 and 1.3741. And that's it. That's a T interval. There's more questions that we got to be ready for, but today that's it. See y'all later. Bye.